Well, welcome back, everybody. Um, I'm counting the number of students that have this. This is what happens, and we're about 12, and that 12, one of them is me, so there's 11. So we started off, I think, with 24. Okay, that's right. What happened one semester? I was down to 2 people coming in at the end, so I don't know. I don't. So let's continue. Oh, just a couple of quick things. Um, Activity 4. Some people are having a challenge with respect to uploading their video. I don't know uh, what could be at least from your end, but a couple of things that other students have done just to make sure that maybe you're not familiar with it. But there is a Canvas app on your phone. Some of you record it on your phone, which is perfectly fine, obviously, or on your computer. If it's on a computer, you save it on your computer hard drive and then upload it. You're done. But if you use your phone, a couple of ways. One, you can use the Canvas app. There is a Canvas app. So if you go to your store and look for it, and when you install it, it's going to ask you for your college, and you put in there, don't put GCC, put Maricopa Community College, and it will find you, and then you'll able to use your Canvas app on your phone. Okay, if you go that route, you use your phone to do a video, then you can simply, upload it on your phone directly, right into the assignment. So that's one way. And alternatively, if you're using your phone, one way is another way is to email it to yourself, get it on your computer through email, check your computer, file it, and then upload in that manner. So if you have any challenges, let me know. We'll see. We'll figure it out. Um, if the if the assignment does not allow you to upload, which it should, and some people are having challenge with that too. Again, I got tech support looking into it. Last resort, send me through Canvas email an attachment of that file, and I would take it, no problem. Okay, but try to get it first through the assignment. It makes it much easier from my end to look at it and grade it right there. Otherwise, I got to go back and forth, back and forth. Okay. So where are we at here? Let's we ended up on slide 24, and today what we've been talking about is how the electrons. Now our model is this, just to refresh your memory. We have the nucleus, which has a proton and the neutrons in the center of our model. And then we had the electrons around it orbiting like our solar system, but in a three-dimensional mode, okay? We thought at one time that they were just kind of haphazardly just thrown there, but we come to realize that they are in specific energy levels. And so there are 7 energy levels, also called shells, which are consistent with the 7 periods of the periodic table. Period 1, 2, 3, all the way down to all of number 118 periodic table, element, I should say. Now, we also determined that within the energy levels, there are sublevels, which are called orbits. And this is where the electrons, based on their model, exist. And now there are 4 types of orbits. Is the S orbit, the P orbit, the D orbit, and the F orbit. So at this point, we have 4 types of sublevels, or what we call orbits. Now, the first energy level only has one type of orbit, and that is the S. And then the second has the S. Now, everybody, 1 through 7, has the S orbit. So you can see in that graph here, that table, that period 1, energy level 1 has the S, and it goes all the way down to number 7. The P orbits are introduced in the second energy level, and that is the second period on the periodic table. And then the third also has the S and the P. And let me back up. The P comes into the second energy level. So from energy level 2 down to 7, we have the P orbits. And then the third energy level, we introduce the D, the delta, the D orbits. And they also go down to 3D, 4D, and down to 7D. And then finally, the F orbits are introduced in the fourth energy level, and they go down to 4, 5, 6, and 7. Okay. Now, the thing to remember about the D's and the F is this. The D orbits belong, the 3D specifically, belong to the elements that actually start on period number 4. Okay, so number 21, element number 21 is in period 4, if you look at the periodic table. And that's where the D orbits begin, because I had stated and showed you on the periodic table, which I'm going to show that again. Here, I said the first two columns, think of those as the S orbit. And then starting with element number 21 and going across to 30, those are the B like in Baker, elements. They have a specific name, which we're going to learn about them. But there are 10 columns there, okay? And then starting with Roman number 3A, we call that the P elements. And guess what? There's 6 columns there. And then finally down at the bottom, we have the F, starting with number 55, element number 55. And there are 14 columns there. And so the D, the 3D specifically, which belong to the element number 21, which is in period 4, the D's begin here, but because of the mathematics involved in their theory and all this going on, the energy level for the D orbits of number 21 actually begin in the third energy level. And hence, that's why you see 3D go in there. Number 39, its D orbits belong in the fourth energy level. So it's essentially, when you get into the D elements here, is you look at what period it's in. So S number 21 is in period 4, and you just simply subtract 1 from the period. So it'll be 3D. For number 39, it's in the 5th period, it'll be 4D. So when you hit number 55, then the F electrons come into play, but only when you get there. So on the same analogy we just did with 21, we do the same thing. We realize that here that number 58 is in the 6th period, but the F orbits actually come into play. They exist in the 4th energy level. So when you get to number 58, and that would be F1, superscript 1, it would be 4F1. So you simply subtract 2 from the period it's in. Okay, so that's why that number looks like it's out of sequence. It really isn't. It's still in sequence. It's just that the energy level for those orbits are either 1 energy level less than the period in, or 2 for the F. Okay. So look at this. You can do the configuration as given here. Memorize that: 1s, 2s, 2p, 3s, etc., or use the periodic table, because I think the periodic table is a lot quicker. You can see the trend on the periodic table, and I'll show you a slide here in a bit to demonstrate that. Okay, so be able to do at least the first 20 configurations, electron configurations. Now, when we look at carbon, its electron configuration. Now, the format for the electron configuration is given here, 1s2, okay? So the 1, the coefficient 1, corresponds to the energy level or the period, okay? The superscript corresponds to the number of electrons in that orbit. So we have the first energy level, which has the S orbit, and that is full. So because remember, we can fill up every orbit can handle 2 electrons. Now there's only one s orbit, but the p has 3 orbits, so we can fill up 6, and the d has 5 orbits, so we can put in a total of 10, and the f has 7 orbits, so we can put in a total of 14. Hence, that corresponds to the columns we talked about in the periodic table. Okay, and so that is the electron configuration of carbon: 1s2, 2s2, 2p2. Now, notice what we talked about, which is called the valence electrons, and that is the outermost shell. So if we think about this here for carbon, it has 2 shells. We had the first shell, number 1. In the first shell, there are 2 electrons that exist in the s orbit. Okay. Now, when we start adding more electrons, that first energy level is full. So we have to create a second energy level. And in the second energy level, there are 2 orbits, the s and the p, and we fill them up in that sequence. We fill up the s first, then the p, then the d, and then the f. So in the second energy level, there's only 2 orbits, the s and the p. So we fill up the first one, the s, so that would be 2s2, okay? And then we fill up the p, we continue across the periodic table, and we see that carbon is in its position, it's in the p elements, it's in the second column of the p elements, and that makes it p2, okay? That's how we can use the periodic table. And I'll show you here in a second a periodic table that shows you all that information. So in the outermost energy level, we call that the valence electrons. That is what's all the action happens. That's where all the chemical action is happening with the electrons on the outside. Nothing's happening with the electrons on the inside. It's on the outside. So we know that carbon has 4 valence electrons. If we look at the periodic table, look at your periodic table, find carbon, number 6, and look at the group number it's in. It's in group Roman numeral 4. Okay, so that group number tells you how many valence electrons it has. Also, when we do the electron configuration, you can see here that there are 4 valence electrons that occupy the second energy level. Of those 4, 2 of them are in the s orbit, and the other 2 are in the p orbit. Okay. All right, so we've gone through this earlier, okay? And level 1 has 1 orbit, the s. Level 2 has the s and the p. Each box represents the orbit, okay? Each little box. So you can see there's 1 box for the s. The p has 3 boxes because there are 3 orbits. The d has 5 boxes because there are 5 orbits, and the f has 7. Now, within each box, you can put 2 electrons, okay? Only 2 electrons. And so you can see here that as we start filling up the electrons, which I'm going to designate with an arrow, and I start with hydrogen, and this arrow represents an electron. So that's hydrogen, 1 electron. I go across the periodic table, I fill in another electron in the s orbit, okay? And that is helium across the periodic table. Element number 2. And as I continue around the periodic table, element number 3, which is lithium. Lithium has 3 electrons. And so those 3 electrons, we're filling them up first with the lower level. So 2 of those 3 occupy the first energy level. And so that leaves 1 electron for lithium, okay? And so 3 arrows represent 3 electrons. And the other aspect about this, if you look at lithium in the periodic table, guess what? It's in group 1, okay? Which tells you that being in group 1, there is 1 valence electron. And that one valence electron on the outermost shell is in the second energy level. Okay. We go across to beryllium. That's Be. That's element number 4. Okay. Well, we're going to need a fourth electron, and I put them in different directions simply because a simple a rule in filling these orbits at one, they're not going the same direction. They're actually going in opposite directions. And so beryllium has 4 electrons. Okay. The level 1 is full, and the other 2 must occupy the second energy level. And guess what? It's in the second column of the S elements from that periodic table I was showing you. And the other aspect is this, beryllium, which is again number 4, element number 4, is in group Roman numeral 2, 2A. That tells you there are 2 valence electrons. And sure enough, there you go. It's in valence electrons, 2 of them. Valence electrons, in this case, those 2 occupy energy level number 2. So continue across the periodic table. The next one is number 5, which is beryllium. Okay. And so now we're in the P elements. Okay. In the P elements. So here, its electron will start occupying the P. So we have a 2p1. Beryllium is in Roman numeral 3a. Okay. Which tells you have 3 valence electrons, and they are in the second energy level. There's 3 arrows in the second energy level. 2 of those electrons occupy the s orbit, and 1 of them occupies the p orbit. Okay. And so the train continues. The next one is carbon, and I fill in all the p orbits first before I backtrack to fill up this. Right. Let me state it this way, just can fill up all the 3 P's, fill them up first before you backtrack to double up. And so there's carbon, okay? There's sulfur, nitrogen, next one over. And then we have oxygen. Now all the P's are full, so now I can go put double up. Okay, there's oxygen, okay? And then I continue to fluorine, okay? And then finally, I end up with neon. Now, neon has 10 electrons. That's element number 10. Do we not have 10 arrows here? Yes, we do. We have 8 of them on the outermost shell. Okay, of those 8, 6 of them are in the P orbits, 2 of them are in the S orbit. And then the other 2 on the inner orbit, the 1 level, the first energy level. Okay. And so what's happened here now is neon, because it's obtained that magic 8. That's important to remember, the octet rule. Because of that, makes it a noble gas and very inert. Okay, because all the orbits are full. Now, in order to go to the next element, which is number 11, okay, which is sodium, we need to go to the next energy level to fill in the electron for sodium. And sure enough, yes, find sodium number 11 on our periodic table. It's in the 3rd period. What's the other thing you notice? It's in the first 1A group, which tells you there's 1 valence electron in that group. And sure enough, that 1 valence electron is in the 3rd energy level, and it occupies the s orbit. Okay. All right. So that's the sequence of filling these orbits, and we just start with the first level and we just fill them up with the electrons. So, and again, all this information came from the emission analysis of the light, of taking these elements and subjecting them to energy, which made them emit light, which then we analyzed the light and broke it up into the different wavelengths. And then once we had the spectrum, we're able to calculate the wavelengths on these things back calculated and determined what was going on. And we determined that these electrons are coming from specific energy levels. Okay. All right. So to do the electron configuration, you may, in here, notice something. We're being given the elements. Okay. The elements. We're going to be talking about the ions here in a second, but this is simply the elements. Now, if we look at sodium, and we can see that sodium, we just did sodium there in the previous slide with the arrows. That is the electron configuration of sodium: 1s2, 2s2, 2p6, 3s1. Okay. By looking at the electron configuration, you can see that the valence shell, which is in the third energy level, is, I've highlighted that. That is the valence electron. And sure enough, it's in group 1. It has one valence electron. Oxygen. If you look at the valence number of valence electrons for oxygen on the periodic table, oxygen is in group 6. Okay, 6A. And that tells you that it has 6 valence electrons, not total electrons, but the number of the outer shell, the valence shell. And of those 6, 2 of them are in the s orbit and 4 of them are in the p orbit. Calcium, okay, has 2 valence electrons in the 4th energy level. Calcium, if you find it in the periodic table, it's number 20. Calcium's in the 4th energy level, 4th period. And it's in the 2nd column. So very quickly, I can write 4s2, okay? And the rest is filled up with 1s2, 2s2, 2p6, 3s2, 3p6, okay? Which, by the way, is the electron configuration of argon, number 18. All right, and then chlorine, its valence shell is in group 7, okay, group 7A. Chlorine is number 17, element number 17 on your periodic table. It's in group 7, which tells you, sorry, I made a mistake here. I forgot to include the the s orbit. Here we go. It's in group 7, which tells you there are 7 valence electrons. Okay, 7 valence electrons. Now, give this some thought here. Okay, as we look at this, we see that sodium, remember on the 3rd energy level, we have 3 types of orbits. It would be 3s, 3p, and 3d, right? So if we look at sodium, it has 1 valence electrons, but also included is the fact that there is also a 3p orbit available and a 3d orbit available. So there's quite a bit of space there, okay? But what would tell you would be easier for sodium to do? One, to fill it up with all those electrons, or simply get rid of that one sitting there all by itself. What does your intuition tell you? From an energy perspective, for sodium, to get rid of that 1 valence electron, or have to add in 1 more to fill up the s, and then I got to add in 6. So I got to add 10. I got to add 17 electrons. Okay, to fill up the 3 energy level. But what does your intuition tell you? Would it be easier to do that, or to get rid of that 1? Those of you with kids, you got a lot of kids, which is easier, get 17 kids into a bus or take one of them out of a bus? For me, with all these kids, I'm telling you, it's a lot easier to take one out than trying to get everybody in the bus, okay? So that's the point here, that for sodium, instead of having to, from an energy perspective, kind of fill up the rest of it with 17 more electrons from an energy perspective is not very energetically favored. It is easier for sodium to get rid of that one electron than to pick up 17, which is what happens. Okay. And once we do that, and we no longer have this full, we release that one electron. The next shell in, guess what, is full. And now sodium has lost one electron. And by losing one electron, it now has a positive charge. And so that configuration, 1s2, 2s2, 2p6, now ends up with a plus charge, the sodium, which is what we ingest when we put sodium in our French fries. We are ingesting the ion. That is called an ion. Okay. And all an ion is an element that's either lost or gained electrons. When you put sodium chloride in your French fries, you are not putting in elemental sodium. That would be a big mess and get a little explosion there. Okay. You are putting ions in there. Those are electrolytes, for example. When you drink a drink for electrolytes, you're not drinking the elements, you're drinking the ions of these elements. And these ions have lost or gained an electron. And what they've done, losing or gaining electron, depends on what type of element they are and how stable the product is. And look at this. When sodium metal loses that one valence electron, the 3s1, it loses one electron. Okay, sodium had 11 electrons to begin with. Now it's got 10. So it got 10 negatives, 11 positives. My net charge is still positive. And now the next shell in is full. How many electrons in the second energy level now? 8. The magic 8. The octet has been fulfilled when sodium loses an electron. Okay. Now go at the other end of the spectrum. Let's take a look at chlorine right here. Okay. Now, chlorine, its valence shell is 3s2, 3p5. Okay. So it has 7 valence electrons. And so when chlorine, it has a choice here. Again, think about it in terms of energy. Is it easier to remove 7 electrons from an energy perspective? Because every time you move something like that, it takes energy. Or is it more from an energy perspective easier to put one just back in? Well, in this case, what does your intuition tell you here? Would be easier to get rid of 7 or add 1 to give you 8, total of 8. Who wants to take a shot at that?
Add 1.
Exactly. Add 1. Now, keep that in mind. Here, the scenario is it's energy perspective, chlorine's going to add 1. Sodium, energy perspective, get rid of 1. Okay? Get rid of 1. Now, in this case, when chlorine picks up 1 electron, that 5, guess what it becomes? It becomes 6. The 3p5 becomes 3p6. Now I have, guess what? 8 valence electrons now. And I created an ion. I have picked up an electron. Chlorine has, 17 electrons to begin with. I pick up 1, now it's got 18. It still has 17 positive protons, but now it's got 18 negative electrons. My net is -1. And so I've created, by picking up an electron, the ion with a -1. That's the superscript -1. That is, again, an ion. Okay. That is what, when they combine the sodium ion and the chlorine, or now we call it change it a name now. I'll say more about that in a second. The chlorine becomes name-wise chloride. Notice the difference. INE represents the element. The IDE represents the ion. Okay, so you would see if you were given a words to take and convert to an electron, a chemical equation, it would say sodium chloride would tell you I have a compound with sodium ion and the chloride ion. You won't see it as sodium chlorine, okay, because chlorine is the element. And that is true not only for chlorine, but for fluorine. Fluorine, when it becomes an ion, becomes fluoride. You're familiar with fluoride. You brush your teeth in the morning. Some of you use fluoride, IDE. You're not brushing your teeth with INE, fluorine, okay? Bromine becomes bromide. Iodine becomes iodide, okay? So two things, name change when it becomes an ion. Second of all, what type of element is chlorine? Is it a nonmetal, a metal, or a metalloid? Anybody know?
It's non-metal.
Exactly. It is a nonmetal. You will find this is chlorine. Remember, everybody in the same group has a similar type of reactivity. So fluorine, chlorine, bromine, iodine, they're all in group 7. They all have 7 valence electrons in the outermost shell. Yes, those valence electrons would be different energy levels, but the same thing. They're just in a higher energy level. Okay, fluorine is in energy level 2. It's valence electrons. 3 for chlorine, 4 for bromine, but they all share the same property in that they have 7 of them. So everybody in that group is going to want to pick up an electron. And guess what? All of those are metals. You will find that that's why, nonmetals. That is why nonmetals tend to gain electrons because they are very close to the noble gas configuration. Okay. And by gaining electrons, now they become electronic wise more like the noble gases. And that means that the octet is full. On the other end of the spectrum, the metals like sodium tend to lose electrons, okay, much more readily because one, they're further away from the noble gases, okay? And by losing electrons, they become positive. And now the ion now has an electron configuration like the noble gas behind it. So a little trend you'll see is the noble gas, the nonmetals by gaining electrons have an electron configuration similar to the noble gas in front of it. The metals by losing electrons have an electron configuration similar to the noble gas behind it. Okay, and that's the driving force of these reactions, gaining, losing electrons to put the products more in a more stable state with respect to the electrons. Sodium metal is very unreactive. In fact, it's so unreactive that you cannot even put it out here at my desk. You know, we actually have to store it in oil, mineral oil, because it won't react with mineral oil. And if you put it out in the atmosphere, it will react spontaneously with any vapor in the air or any moisture. So it's so reactive because sodium is driven so hard to get rid of that electron that's sitting there in the S31 position. Okay, so that's in a nutshell the the driving force of a lot of chemical reactions, be it this type or in some other types. So we'll get to more of those. Now, this again is a summary. I mentioned earlier with that periodic table about the S electrons, the D elements, and the P elements, and this kind of breaks it down for you again, so you can see. Notice in the S elements, there's 2 columns. In the P elements, they are 6 columns. The D's have 10 and the S have 14, which represent the number of electrons that we fill in as we fill in the S, okay? The S, the D, the P, and so forth. Now, I have talked about the driving force of having 8 electrons in the outermost shell become noble gas, okay, which I've highlighted here in red. The only exception to that is helium, which I put in yellow here, okay, because at the maximum they can handle is 2. So all the other noble gases from neon down have the octet rule, the octet 8 electrons around the outermost shell. Helium only has 2, so it has a separate rule. It's called a duet. Okay, it has its own duet rule, but all the other elements have 8. So they put helium underneath group 8 simply because the outermost shell is full. So keep that in mind. It does not have 8 electrons around it. It only has 2. Okay, and it's unreactive, so that's why it's in that column. It's a noble gas. All right. Now, in this table, this is the electron configurations I'll put for you in with respect to the element. And so we start with hydrogen, upper left corner, we have 1s1. Okay. Hold on one second. Give me 2 minutes. Something's come up. I got to do something real quick. Take a look at this slide. Hey, my apologies. I'm back. All right. So if we look at this table that I'm giving you here, you'll see that the electron configuration at each element, at each point is given for you. So we start with hydrogen, upper left corner, 1 electron, 1s2. If we go across to helium, top right corner, 1s2, 1s1 for hydrogen, 1s2 for helium, okay? Now, as we fill the electrons, in other words, sometimes I've seen things like it's written, I got something going on here. Oh, can anybody hear me?
Yes.
Yes, we can hear you.
Yes,
Yeah.
I can hear you.
Something's going on my end. I may have to, it's telling me it's not responding. Can everybody's, all right, let's, okay.
I
I'm
cannot
gonna,
see you.
yeah, you cannot see me exactly, but you can hear me. Well, this is what I gotta do. I gotta close it and then I gotta reload it. Okay, so give me 5 minutes to close the program and then we'll be back online. We're slide number 29. Okay.